name is Jose Navarro, and I work for CTTC, a research center located in Spain, specialized in telecommunications and geomatics, which is the division I work for. Well, I would like to thank the organizers of this conference for inviting me to present the work I've been involved with lately, which is H2020 project called MOMIT, which stands for, as you can see in the lower part of the slide, multi-scale observation and monitoring of railway infrastructure threats. Okay? The purpose of this project is to show how remote sensing techniques and data might help the monitoring of railway infrastructures for maintenance and prevention processes, yes, using multi-sensor and multi-scale data. Okay. Oops. Okay, now, the consortium of this project is made of 6 companies and institutions. 3 of them are Italian. EGEOS, the first one, is the coordinator of the project. Then there's also NEET. And finally, which is also the final user of the project, we have RFI, which is the national agency managing the Italian railway infrastructures. There are also 2 Spanish companies or institutions. The first one is the Universidad de Alicante, and the second one is CTTC, for which I work, okay? And to close the consortium, we have a French company, which is Terabin. Well, to show how remote sensing might help the monitoring of these railway infrastructures, up to 6 demonstrators, which a demonstrator is in fact a set of tools and data, up to 6 demonstrators have been defined. You can see them here on the list, and well, there's something of them about which I can't say nothing because they fall out of my field of domain, like electrical system monitoring or safety monitoring, but in other cases the goal should be clear for us, like the monitoring of civil structures, like bridges, for instance. We'll have in mind what happened to that Italian bridge a few weeks ago, okay? Well, out of these 6 demonstrators, CTTC and myself is involved only in development of one of them, which is the one that deals with ground movements nearby the infrastructures. And more specifically, well, ground movements here stand for any kind of deformation process that the terrain is undergoing. Whatever these are, landslides, subsidences, deformations produced by thermal effects or whatever, okay? Deformations, in fact. So, more specifically, we have developed a set of applications for this demonstrator, and the first one deals with the detection and updating, where updating means detection once again and once again as many times as you need, of active deformation areas, which we will call ADAs from now on to shorten my speech, using information derived from Sentinel-1 imagery, more specifically point scatters. I have to say that in spite that this is a new application, what is really new is the methodology that we at CTTC have implemented in this new tool, okay? This methodology was introduced last year by one of my colleagues at CTTC, Navarro, and her colleagues also, and you can, if you are interested in the details, you can get this paper for free because it's freely downloadable. It's available on the internet, okay? So, to sum up, this tool is just implementing this methodology. I'm not doing anything new. What is new is the methodology described in this paper. Well, the application, the ADAfinder, as we call it, takes the point scatters I already mentioned, coming from Sentinel-1 imagery, and creates a map where the areas where deformation processes are taking place are located. And we also provide with an assessment of the certainty about these findings. This certainty has been classified in a 4-level, in 4 degrees, going from, well, we think that here something might be happening, which is shown as great areas in the figure, or we are completely sure that something wrong is going on here, which is shown in green patches on the images. In between, there are two more levels, okay? Having this classification and this geographical location, the operator taking care of the monitoring of the railway infrastructures can prioritize within the actions that have to be taken in order to correct any possible problems showing up close the infrastructures, okay? Well, the goals of this application, well, the first goal, we could say, was to automate this methodology already developed. But automation by itself is not a goal. We want to automate because there are other goals behind. And the first one is to avoid the mistakes that human processing introduced in any manual procedure. In fact, even the creator of the methodology, Navarro, told to me that it was very easy to commit errors, not because the methodology was incorrect, but because it was complex. It was a lengthy process, prone to errors. So automating this procedure would remove immediately the chance to make any mistakes. So this is a very important reason to automate the task. Additionally, of course, we wanted to reduce the amount of time needed to produce this information, because then it is possible to play a little bit more, turning the parameters that control the results. Well, we also wanted to avoid some problems concerning with the unavoidable variability of the data files provided by several, let's say, data providers. But, well, I'll talk about this a little bit later on if I have enough time. It's not exactly the most important part of the talk, okay. Well, this is a sketch of the algorithm or the methodology as designed by Navarro in his work. Okay, I'm not going into details, because if you are really interested, you can read the paper. The reference is also given at the end of my own paper, so go there and read it if you think it might be of interest to you. I will say just that there are three big blocks here. In the first one, there's some filtering tasks take place just to remove those points that for sure are stable, so will never be part of an area that is suffering a deformation process. In the second block, the ADAs are identified, and the third block is the quality, the certainty assessment of these findings. Well, just to comment on the complexity of the application from the mathematical standpoint. This is a joke. I mean, this is something very simple, and there's even a software engineer like me with a poor mathematical education was able to implement a computation of several standard deviations, autocorrelation functions, and so on. So the problem to make an efficient application lies somewhere else. If you take a look to the methodology, you'll see that either directly or indirectly, the words group of points are mentioned every now and then. This is, for instance, when we talk about removing isolated points, when we talk about spatial outlier, which are in fact groups of points that with so few points that will never become an ADA, or again, when groups of points so populated that might be candidates to become an ADA have to be identified. So it looked like it was very important to find the right way to identify these groups of points, since otherwise the performance of the application wouldn't be as good as we were expecting. So, before going to the details on how we increase the performance of the clustering algorithm, I will tell you what's our approach to this problem, and then how we decide to solve or how to identify these groups in an efficient way. What we have for input is just a bunch of points, the points scatterers. a set of x and y coordinates and some extra attributes that will be used to perform this grouping of points. Okay. However, one of the parameters that the operator might set to control how the algorithm behaves is the distance used to consider that 2 points are close enough as to become part of a group. This is a threshold distance. Then if we go to the lower part of the image, when we see the same points that are drawn in the upper part, we can see that we have drawn some arcs connecting points because this couple of points are close enough to each other, meaning close enough that the distance between them is below the threshold distance set by the operator. Immediately, we can think of this set of points as a graph made of a set of disjoint connected components. If we view the data as a graph, then we apply a classic technique to identify these connected components, which is using an algorithm which is called DFS or depth first search. Okay. So that's our approach, interpreting data as a graph instead of being an unconnected set of points. But well, yes, we want to see data as a graph, but in fact we have no data, we have no information about the arcs in our input data because they don't exist. In fact, what we are doing is to imagine that we have a set of virtual arcs defined by a mathematical condition, which is the distance between 2 points. So, to find these arcs, we must compute on the fly the distances between these points. Well, computing these distances might be done in many ways. The most stupid and naive one would be to compute the distances between all the pairs of points in the data set. Well, just imagine that we have a data set with 1 million of points. This would mean to compute 1 followed by 12 zeros distances, which is clearly unaffordable from the computational standpoint. This is a quadratic approach, okay? So we must avoid a solution of this type. So what we did was to sort data. Sorting is miraculous in most cases, okay? We sort the list of points using 2 criteria. First, the x-coordinate, and then the y-coordinate. And then look at the figure, please. If we assume then that the points located above the arrow have already been processed, and we are processing the one whose coordinates are, let me see, 4.1 and 2.4, we know that all the points located below the green bar on the left will never be close enough to the point we are checking because the distance between the x-coordinates are already beyond the limit. The same happens if we then add an extra condition, that is that the y-coordinates, when we compute the actual Euclidean distance, as soon as we go beyond the first point that doesn't match the distance criteria, we don't need to check them. We don't need to check them because the data is sorted. When using this approach, we might reduce the number of distance operations drastically, and then improving the performance of the algorithm in a rather noticeable way. Well, since I've been warned that I only have 3 minutes left, I will skip this part. I wasn't sure about the possibility of talking about this. It's not important, so it's no problem if we skip it, okay? Well, about the finish. We have produced this software using C++ as the language of reference because this is a compiled language generating executables that are much faster than the software that is written, for instance, using interpreted language as Python. We have also put every little bit of effort to make the software portable. So now it can be executed on Windows and Linux. And even when user interfaces are involved, these are also portable because we have used the Qt5 framework, which is portable by itself. Okay, the software has been produced in 3 different shapes. The first one being a library that you might embed in your own software just by calling a single method, so you can access the functionality of detecting ADAs just calling one method. It's that simple. But also for production purposes, we have delivered 2 applications in 2 shapes. The first one being a command line application, which might be embedded in a batch file and then run in an automated environment when there's no need for human intervention. And finally, when the operator needs to fine-tune the parameters controlling the behavior of ADAfinder, a GUI application might be used, which, by the way, has this looks. Okay. Performance. The one who devised this methodology needs about 60 minutes to process 1 million points. The application needs only 3 minutes. This would mean an improvement of reduction of time of 20 times. Okay. However, since this person says that she's no master of GIS tools, she estimates that a conservative estimation of how much would take to process the same data set to someone who really masters GIS would be about 30 minutes. This means an improvement of 10 times if we take a look to what is needed to process data manually. Sorry. These figures come from a regular computer, nothing special, but the application is so fast and so reliable now that it's being used in regular tasks by our colleagues at CTTC. Well, concluding, how much time do I have? It's over. Concluding, I won't go again through the list of features or characteristics that I have explained to you just a few seconds ago, just to comment that at the time of writing this paper, there were 2 applications in the process of development and now are finished. The most important, I will only talk a few seconds about it, is ADA classifier. This task starts, this software starts when ADAfinder stops. And its mission is to try to classify the ADAs found previously to state whether they are landslides, whether they are subsidences, whether they are sinkholes, or up to 6 different categories of ground movements. The methodology is still under development by the University of Alicante. More precisely, the developer is Roberto Tomás. And well, he thought, however, that in spite of not being finished yet, it would be interesting to implement the current version of his methodology. So its results could help to refine the methodology, creating a feedback between the research and development. Well, that's all on my side. If you have any questions that I might answer, just think that I'm just a software engineer implementing the ideas of someone else, I will be very pleased to answer them. Thank you very much for your attention.
Thank you very much, Jose. All the big questions, but we don't really have much time for questions. Brief question and brief answer, if possible. Thank you very much. Tell us, please, for the selection of graphs, did you use a graph mathematical theory for the optimization of graphs?
Повторите вопрос, пожалуйста.
For the selection of the points, do you use a mathematical theory of graphs for the optimization? Or are they selected randomly?
All the points in the data set are involved in the search of connected components. Well, that's not true. Only those that have survived the filtering steps of the algorithm are taken into account. So those that, for instance, have a standard deviation of their velocities below a threshold are not included in this procedure. The remaining ones, yes, are taken into account.
Так, хорошо, последний вопрос.
Okay, the last question then. I understand that the principal theme of your subject, of your presentation, was the structuring of the deformation points, or as you call them, point scatterers. Is it the same as the persistent scatterers? And which series of images is required? How many images do you need for reliable detection?
I have no idea, because the information that arrives to my software has been already processed by some other colleagues in the chain. Okay, so what I already get are the persistent scatters. Sorry for the miswriting. Okay, so I'm sorry, but I can't tell you.
Okay, I see. So,
thank you for your question.
Спасибо.
Thank you. Thank you, Jose, for a very interesting presentation. Moving on to the next speaker.